Hello and welcome, YouTube, and all my mini student. So, yesterday we talked, or rather the last time we were all together, we talked about how graphs are just data structures that point in all kind of different ways. So today, what we are going to find out and talk about is how to find the earliest ancestor in a graph. So basically, how far back in time can we travel? So pretending that this was a binary search tree, right?
Yeah.
And we go back and back and back and back and back and back and back ad nauseum. We would eventually always return to the root node, right?
Yeah.
So this time we have a little bit more interesting things going on.
Going all over the place now.
We're going everywhere. We don't necessarily know any of these relationships for certain. So we're going to try and find, with our starting node, which could be here, how far back do we go until we reach the beginning of the family tree, so to speak.
Okay.
Are we all excited?
Yeah.
Woo! All right, so the first thing we need to do is instantiate the graph.
Okay. So we don't have to make a class here then.
Right, because we have created the class, we've imported the class of graph. So now we're just going to say,
Okay. So I'm exhausted. So what do I do now?
so,
Graph?
yeah, we're going to create a graph
Okay.
so we're going to initialize the class. So we're going to say, in my husband's, we have lineage equals graph.
I'll just say line. No, that doesn't look right, does it?
No, not really.
Lineage.
Tree,
About the same.
lineage. Yeah, it's fine. That's fine by me. Lineage equals graph. And then you invoke it. Perfect. So because we are working with a graph and we're going to be working with all the stuff that we defined last time inside of our graph, right?
Mm-hmm. Do I need to pull
Awesome.
aside?
Um, it could help.
Okay. Okay.
So we've got all these great things that we're going to be working with our graph. So give me another line. On line 7, we're going to start with our for loop. So for parent and ancestors.
Helps if I can type. And ancestors.
So we're going to loop through these things and add our vertexes. So we're going to basically create the graph if the graph isn't there, right? So if parent 0, not in lineage, because our ancestors are in pairs, colon, then we're going to add it to the lineage. So we're going to add our vertex.
So it would be graphs.
Lineage,
Oh,
because lineage is the name of our graph.
okay. So lineage dot add vortex.
Yes, except we have to spell lineage correct.
Oh, thank you.
No problem.
Lineage add vertex.
And then the vertex we're going to add would be parent 0.
Okay.
So if it's not in our ancestors, then we're going to add it to our ancestors. So if it's not in our graph, then we're going to add it to the graph. So we've done the first parent. Now most things have at least 2. So if parent 1 not in lineage.
No. 1 not in lineage. Okay, I'll get it together eventually. Hopefully before the night's over.
So then if that one's not there, then
so
logically
the same thing, lineage, and then add or dot add vertex, whatever you want to call it, and parent. No,
it's going to be one of those nights. All right.
yeah, I'm sorry.
It's all good.
Parent 1. Okay, we did that.
All right. So now we've just checked and made sure that this is all good. All right. Now we're going to go over and remember what we used last time? Go all the way back to outside the for loop. So we had paths. And paths were our
Set.
Yeah, our paths were the way that we got places. So lineage dot.
Oh, okay. So I'm making path lineage.
Yep. Lineage dot depth first recursive.
Okay, so that was depth for the DFT recursive, right?
Mm-hmm.
Make sure. Yeah, okay. Just want to make sure I was doing it right here.
And so what sort of thing are we going to put it? So our depth first recursive had
a starting vertex, and well, the visited would stay none.
Right. So our starting vertex would be our
that would be the starting node. Okay.
Right. So we're going to have this little like wonderful list of things that we're going to go through. All right. Now this one I feel like you'll like as a data scientist. This is my husband's being smart. So max length path equals No. Max length path.
Oh.
Yep,
the variable. Okay.
Yeah, the variable.
Okay.
Max length path equals max parentheses list comprehension. We'll put a list comprehension in there.
Oh.
Yep. Length path.
Length path or len path?
Len path.
Okay.
For path in paths.
In paths?
For path in make this paths with an S because it's going to be a lot of stuff.
Okay.
And then this is going to continue. So outside of the max. Yep. If length paths.
Okay, so we're going on a new line then.
No. Keep going.
On the same line?
Yep.
Okay, that doesn't sound right to me, but okay, I'm following you.
If length path greater than 0, else 0.
So if len path.
Paths.
Oops.
Paths.
Change. No, okay.
Greater than 0. Else 0.
All in the same line still?
Yep. That's the same that's the same face I made. But yes. Else 0.
Okay, do I need a colon here or no?
Nope. Else 0.
He's doing something I ain't never done before. So. Now a colon? No?
That's all done. All done. So basically he's saying the maximum length of the path is going to be the longest path that's in our list comprehension if the length of paths is greater than 0. Otherwise, it's going to be 0.
Yeah, just the code though doesn't. Yeah, I've never done anything like that before. Having it all
This,
in one line like that.
I have seen this done on occasion. My husband loves doing these things.
Oh, he likes to confuse everybody.
Oh, he loves confusing me. It's like one of his greatest joys in life. Oh, I was hoping Doc was going to be here for this because I wanted to hear her like explain this. But that is essentially what it is and what it does.
I mean, I knew about doing the list comprehension before that, or yeah, list comprehension, but I
The
never
rest of it,
do an if and else in the same line like that.
it looks a lot like a ternary from JavaScript because sometimes we'll just be like variable question mark action colon action.
Okay.
So it reminds me a lot of a ternary in JavaScript. So it's the maximum of these things if this thing is greater than 0. Otherwise, the path is 0. Like how so husband smart. Love husband. All right, now we got a new line. And we're going to go with possible equals a list.
Just an empty list?
Yep, empty list. All right, new line. For path in paths, this is another one. If length of path,
On the same line again.
no.
Oh,
For path
okay.
in paths, colon, new line. If length path is equal to max length path, potential dot append path.
Huh?
So colon, new line,
Okay.
possible dot append path. So what we're doing is we're saying if the length of any one of these paths
Path?
is this single path, for path and path. So we're saying
Okay.
if any path, right, is as long as the maximum possible length. So we went through and we found out the maximum possible length is 7. We're just going to see if any of these paths over here, how many of them are possible. So remember our paths last time was like
So it's
K.
the placeholder. So when it finds a
Yeah.
new one, then it's going to put it in there.
No, it's not a new one. It's going to add to it. So remember last time we were finding our paths and it was like K1, V1, V3. So we're
Yeah.
finding all of the paths that end in V3, but we want to see which one is the longest, right?
Okay.
So this one's short. So this is our list comprehension that's going to find our maximum length. So we're going to see V1, V2, V3, and we're going to go, oh, cool, look, we've got 2 that are 3 long, right? So this will be our possible paths to find our maximum length. So we'll find our maximum length here is 3. 1, 2, 3, 1, 2, 3, right?
Yeah.
So for every path that is still stored here, we're going to look at it and we're going to see and we're going to basically add only the paths that are 3 1, 2, 3 that are 3 long. Okay?
So it's going to go like through the first path and it's going to find the longest in there.
Yep, that's this one. That's line
That,
16.
yeah. And it's putting it in and then 20 is going, and 20 and on is going, putting it in the possible.
Yes.
And then it goes on to the next path and then sees, is that one larger than
It's
the pre.
no, the
It
line
actually.
20 is finding all of the ones that are equal to the longest.
Okay. Okay.
So if our maximum possible path is 3, that's the longest thing that we're going to have in there, right?
Yeah.
It's
Okay.
going
I
to have
got
a length of 3. So if it's less than that, it doesn't matter. If it's greater than that, that's not possible. So anything that's got the length of 3, we add the whole path into our list of possible paths.
it. Okay.
All right. So now, new line outside of the for loop. If length of the possible equals 1, so there's only one path that is the longest path, right? Then return potential, then return the possible. Parentheses 0, parentheses -1.
One. Okay.
So we're grabbing so because this is set up as a list, right?
You're grabbing the very first one, and then you're grabbing the last one.
Right. So we're grabbing the stuff that's stored inside here. So we're grabbing 0 would be the list, and then -1 would be the last thing in the list. I think we could do 0 and 0, but 0 and -1 also makes sense. So we're just grabbing the path. Else if...
Okay, sorry, I had to turn my heater on.
It's all good.
Wait. Hello, we got to put something there.
Yep. Length of possible greater than 1. Current ancestor equals possible 0, -1.
Okay, so we're doing actually current ancestors. Wait.
Yep.
Okay.
You could do current or current ancestor. I like to make my things as readable as possible. I think he had CA and I wanted to smack him.
Well, current, that's more explanatory than CA, but okay, we'll go with current ancestor. Okay,
Yes.
what
Current
equaling?
equals possible 0, -1.
Okay, 0, -1. Joanne.
And then inside of this else if, we're going to have another for loop. So inside, for path impossible, if path -1 is less than current ancestor, current ancestor equals path -1. And then outside of the outside the for loop right there, good. Return current ancestor. Too far outside. Return current ancestor. And then our final, return -1. So we went through everything and we didn't find anything at all.
Just -1 or -1 in bracket?
Return -1 because that is what they want.
Okay.
So let's walk through what we did.
Back up to the top?
Yep.
Oh, we didn't have to go that far. There we go.
So
the whole thing. There we go.
So first, we said we're working with a graph, please. Then, for the parent of our ancestors, for every pair of our ancestors, if the parent is not in the lineage, then we add the parent to the lineage. If our other parent is not in the lineage, we add the parent to the lineage. Then we find all of the paths by using our depth first recursion, which goes over here, does a whole bunch of stuff, and returns a nice path for us.
I was trying to pull it over so that.
So if we go down.
So this is the one right here.
Mm-hmm. This is going to go and 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 go, and it's going to print out every single one of our vertexes in a circle. In our visiteds, basically. In our visiteds in order. So that's what we've got. So that's going to return those for us. Then we're going to take our maximum length path, doing this list comprehension, first finds, so this list comprehension here will find the longest length of the paths. If there is no length of the paths, oh no! Ah! It's going to return 0.
Yeah.
Which would basically return which would finally end returning a -1. All right, so our possibles, we have an empty list. So now we're going to start creating some stuff. So for path and paths, if the length of the path, and remember our paths from yesterday were like K, V1, V2, etc., etc., etc. So if the length of the path, yeah. So then we're going to take each one of these paths that have been added into possible. So our possible contains essentially a list of lists. If the length of the path is equal to the maximum length of the path, then
we're going to put it at the back of possible.
Right. So we're going to take all of the paths and filter them and find only the ones that match our magic number of length. Then, if we have only one thing in the list, we're going to return our oldest ancestors. We are grabbing, that's what we're doing. I think we're grabbing our starting and our ending ancestor.
Okay.
Then we're going to loop through. So if there's more than one possible ancestor, we're going to, basically we're saying this one goes from K to, 82, whatever it is. The oldest possible ancestor. So we're returning the first and the last. Now for path impossible, we're only comparing the last ancestor. Right? So like if we were to compare 2 family trees of equivalent generations. So we can do this with in any normal family. If you're a normal breeding pair, you generally have children in your 20s or 30s. Most generations in their 20s. In my family, we don't breed until we're like almost 40. No one in my family has children on the male side until they're in their mid-40s.
Wow.
So, looking at my mother's family tree versus my father's family tree of equivalent length, my my fourth for example, my grandfather was old enough, was 97, 99 when he died.
Wow.
And my father was 67 and I was 15. So we have these really big generational gaps. On my mother's side, my mother, well, she was also pretty late when she had me, but my grandmother is now currently 97. She's currently getting there, as opposed to a while ago with my grandfather. So we have a 20-year gap, generally speaking, on my mother's side, and a 40-year gap with the men on my father's side. So, which that means if I go back about 4 generations on dad's side, that's 160 years. And if I go back 4 generations on my mom's side, that's
80.
80 years. So the oldest possible ancestor looks like I'm somewhere in the Civil War on dad's side.
Yep.
So that's kind of what we're doing. We're going, okay, cool, we have these longest paths. How did we get to Ava? Which ancestor is the oldest? That's what we're doing. These are our earliest ancestors, and this is how we find them. If only genealogy was this easy.
Yeah, right?
Okay, so does this make sense?
Yep.
Does the way that we used our graph make sense, and the way that all of this can be done make sense?
Yeah, because when you're dealing with like a family tree, well, I guess you could kind of consider it a binary tree, but
Yeah, kind of like.
yeah, kind of like.
We're using a family tree as an example, but that is essentially what we're doing. Is we're trying to find like the earliest, the most ancient vertex we can find.
Yeah.
So that is what we're doing. The closer to the source that we can do. So that's what we're trying. All right, now social.
Do we have any imports on this one? Can I close the graph or?
Hang on, just give me a second. Let me look at social. We're going to import random and stack.
Okay, so nothing from the graphs.
Nope. So we're going to import random. And then from utils, import stack. Import stack.
Okay, I was just trying to figure out why it wasn't working with utils. And it's capital S, right?
Yep, S-T-A-C-K, stack.
Okay.
Hang on. See, mine's not giving me a thing. Oh, it should be from graph import stack. No, from util. Oh, get rid of the S. There you go. From util import stack. Because we had to use our util to make our stack and queue the other night.
I guess because I don't have util installed on mine. That's what it is.
Trying to figure it out because it came with the graph. It said from util import stack queue, and these may come in handy. Huh. Didn't really look that hard when I was writing these the other night.
That one's not giving me an error. That one works.
I know.
That's weird.
I don't understand. Okay.
Anyway, moving on, right?
Moving on. Looking at our social. So, look at how kind they were. They have created some stuff for us. So, first we have our user. Our user has
A name.
Now we look at our graph. So each vertex of the graph has some information. It has the last ID, which is the most recently added friend. It has a list of users and a list of friendships. So a lot of this has been done for us. How kind!
Mm-hmm. Until you get to the part where it says implement me.
So let's first take a look and get familiar, because this is something that you'll have to do when you're digging through someone else's code. So first, you cannot be friends with yourself.
Why not?
Reasons. Next, you can't be friends with someone twice.
Oh, darn.
And otherwise, they're going to add a, what's that line between vertices called?
Edge.
Woo! So we're going to add an edge between these things. Neat. Then we're going to add a user.
Oops, sorry. I moved it on you.
You did. How dare you? We're going to add a user. So we're going to auto increment. It's not secure. We're going to auto increment to increment the ID assigned to the new user. The last ID is going to be our new user. So self-user's last ID is going to be whatever name we just passed in. And then we're going to set up our friendship key, right?
Yeah, because you're using a set.
Yep, we're going to set up our key, and then there's all our values. Alrighty, so we have our number of users that we're going to create a number of users. We're going to pass in an average number of friendships, do some math, use .random, and create a friendship graph.
Okay.
So, first thing we're going to do, add users.
Okay, I tabbed in on the wrong one.
There you go. So, we're going to have our number of users is the range, is a number. So that tells us we need to use
Num
for I in range.
Okay.
Because this is going to be a number.
So we're doing indexing.
Yep. Well, no, we're not doing a index. This is the number 7. So if you say an I in range 0 to 7, it's going to count to 7.
Oh, okay. Yeah. I'm just so used to doing I for index and then doing the in range. Okay.
It's all good.
So we're not doing length. We're just doing range num users, right?
Yep. And then we're going to use our add user function. Self.add. And then we need an F string.
Add user.
Yeah, self.add user. Thanks.
Well,
self.add
PyCharm for that one.
F quote. So we're going to use our F string.
Oh, okay.
User. Space parentheses. I. Or just user I. Not parentheses, these things. Okay. Curly boys.
Curly braces or brackets?
Yeah, curly boys.
Dictionary. Okay.
Yeah. I, right? And I do believe this has to be double quotes for the F string, because it's not doing the thing for you like it does for me.
Okay. I'm just so used to using the single quotes unless I have to use double quotes. It's not doing anything either.
Okay. So, no, I think mine just changes color because of what I did.
I is a different color, it looks like. I is white and the rest is yellow.
All right. So, that's all we're doing there, is we're just going to loop through and add a bunch of users. All right. That was easy.
Yeah.
Create friendships.
Garfield.
So, what we had last time is our potential friendships.
Which is going to be, well, no, that's not
list.
The average, right?
That's right. It's going to be a list. This is going to be potential. It's going to be potential friendships, and it's going to be an empty list.
Okay. Create friendships.
Yep. So we're going to have our list of possible friendships.
Okay.
It's going to be an empty list. Empty list. All right. So for every user ID, I'm trying not to give you exactly what to type.
For
So for
okay,
every user ID in our in our users.
okay, so that's gonna be okay. So for every ID in users, right?
We're gonna have two different types of ID, so it should be a user ID.
So it should be user ID. Okay.
Mm-hmm.
You said you weren't trying to tell me exactly what to type.
I did try. I did tell you for every user ID.
Oh yeah. Okay.
In users is giving you a squiggly.
What did I do wrong? Does it have to be self dot users? No.
There you go.
It does? Okay.
Because we have users all the way up there.
Oh, okay. Okay, gotcha.
So for every users, so for every friend's ID, in the range
Friendship?
of the user's ID plus 1 and the last ID plus 1.
Okay, so user ID plus 1. So I've got to do this inside and
No, that's
then
fine. That's fine.
that's
In
fine.
range user ID plus 1, comma, that's your starting range. And
Okay.
our last ID plus 1.
Okay, so it's going to be user ID or friend ID plus 1.
Last ID. Do you remember when I showed you the last
Oh,
ID? And was that in something?
plus 1, right?
Yep.
Okay.
So then we're going to add to our list of friendships our user and our friend.
Okay, so what did I do? Friendships. Yeah, okay. Friendships. And then we're
Dot
doing
append.
append.
Yeah. Space.
Oh, I told you I'm exhausted tonight.
It's all good. And now we're going to append a set of
User ID and FID? Or no?
yes, user ID and friend ID. Okay.
Friend ID don't like me.
Because you said FID. I don't know. Why is it giving you a squiggle? Hover over it.
Ah!
Scroll down. Hover.
Unexpected argument. What does friendships have now?
Let's scroll up and
Oh,
see if
did it add friendships? Is that why?
not. Oh, because it's got friend ID right there.
Oh, so I gotta put in friend ID. Okay. So this has to change to friend ID also, or no? I can leave that.
Probably. No, it's going to want friend ID and friend ID probably. Friend ID? Is that why it's doing that?
Nope.
All right. Get rid of the word set.
And the parentheses also the second set, right?
Nope. Nope.
Oh.
Leave that there. There you
go. Okay. That's weird. I guess that it automatically that's telling it it's a set without having the word set in there.
Yep.
Okay.
So now we have made random pairs of friends. And now we're going to shuffle our friendships outside of both for loops. We're going to shuffle we're going to randomly shuffle our friendships.
Okay, so
Randomly.
oh. Just random?
Shuffle. Dot shuffle.
Oh, dot shuffle.
We to randomly shuffle the friendships.
Used that one before. Okay. Our friendship list, right?
Yes, friendships. Yes. So now that we have randomly shuffled the friendships, now we're going to have another for loop. For, and this is from the blah 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 thing. This is from the class. For I in range 0, comma, num users times average friendships floor divide 2.
Num users times average friendships floor divide 2.
Mm-hmm.
Okay.
So that good. Singular friendship.
Yeah.
Equals friendships I.
Like that, right?
Yep, just like that. Self dot add friendship.
Oh, no, wrong one.
Friendship 0, comma, friendship 1.
Friendship and then 0.
Use the
Oh, hello.
comma, friendship 1.
The single one, right?
Yep.
Single friendship. Okay.
And then one last self dot friend added plus equals 1.
Friend added or add friendship?
Yes. Friend added. So we're going to increase the number of friends that we know that we have.
Okay, where are we getting friend added from though? Or we're just creating that one?
Yeah, up there.
Okay,
Up in
because
the
it
sky.
didn't come up with anything.
Mine has things. Mine is not yelling at me.
Out of the add friendship, because it just says self friendships.
Huh. Weird.
Is something different?
Well, then ignore that line. You don't need it.
Okay. So we take it out.
Yes. So then take out self.friend added plus equals 1. Because it doesn't yell at me, but it yells at you.
Maybe you have something else up there in the methods.
No, I think it's just from my husband's. I think
Oh,
he just did a thing. All right. So what we have done is first we added all of our friends and gave them a name of user 1000 of user 1, user 2, user 3, user 4, etc., etc., etc. Then we created a list of pairs with, for every friend in this range, we created a list of potential friendships. And then we shuffled them. We made a real mess of it. And then, for I in the range of the number of users, 7, times the average number of friendships, we're going to say 2 because I'm bad at math. And then we divide it by 2.
gee, I
There,
wonder what you get. 7.
I had to think about it for a second. That's how you know. 7. So they're going to have 7 friends. So they're going to have 7 friendships, not 7 friends. So they're going to have 7 edges, 7 connections.
Oh, okay. off of one user ID.
Yes.
But what if they want more friends than that?
This is just a random chart.
Oh,
This
okay.
is a seeding chart. We're not doing anything other than creating a randomized social network.
So in other words, it's kind of like when Facebook recommends you friends or something like that.
No, this is just a proof of concept.
Oh,
This
okay.
is making dummy data. So this is something that we do in our back end a lot when we're waiting for data science to like give us something. We'll do something like this and make up our own fake data.
Okay.
How we're going to get all of the social paths.
Okay. So we're done with that one then.
Yep, this is all done. Woo! Gold star. Everything works
Woo!
except for your imports. Woo!
Okay. Implement me and then return visited. Okay.
Right.
We can
So
do
we have implemented our stack from earlier. So now is where we're going to use the stack.
that. Okay. So refresh my memory. Let's see. S equals sock. Right?
Yes, S equals stack, not sock. All
Sock.
right. Now we're going to create a method within an internal method. Define get neighbors.
Oh, that was about right? Wait a minute. We already got to get neighbors.
No. This is new.
Okay.
Underscore neighbors. This is
Okay.
an internal function. And we're going to pass it ID.
Just ID.
Colon, return. Return self.friendships ID.
Plural, right?
Self.friendships.
And
Yes,
then
plural ID.
like this. Okay.
Yep.
That's it?
See, yep. Find get neighbors, self-friendships ID. Good. All right. S dot push user ID. So we're going to add our user ID into our stack. Push
Okay.
user ID.
Okay. S dot push. What now?
User ID. So we're going to push our user ID into our stack. IE
No.
parentheses.
Parentheses. Okay.
There. So we're going to push our user ID into the stack. Pancakes. So while s dot size
Well, S dot size
is
is
greater than
greater.
0, user equals s dot pop. So we're going to pop something off of our stack, and that's going to be the user that we're looking at. If user not in visited, you're such a handsome baby. I'm petting your chest because you're cute. Gosh. Okay, if user not in visited, then we're going to create the key.
Okay.
So visited with our key of user is going to be an empty list. So
Okay. So, well, I can't use key, so I'll use K.
no, use visited.
Oh, visited. Okay.
Right. And then the key is our user. There you go. User.
I'm trying to put key in there again. Yeah, it's one of the days. User.
User is an empty list. So we've created our brand new key of our dictionary with a whole bunch of empty values. Right? Our value is currently an empty list. Woo! For neighbor in get neighbors user.
Inside the if.
Yep. For
Or
neighbor
and
in,
neighbors.
then we're going to pass our user into that.
Okay, as a list.
No, just user right there. See, we have our user that we popped off. So
Oh,
now we're going to put that into there. And we're going to get all of the neighbors. And then we're going to add it to our user. So, right, we have that key that we just made
the
with our
visited.
user. And now we're going to add all of their friends to it like that.
Dot append or
Hang on, s.push. So for neighbor, visited neighbors user s.push. So first we're going to add the neighbor to our stack.
okay. So we're gonna do user here.
Neighbor.
Neighbor, okay.
So we're going to add the neighbor to the stack. And then we're going to add the value neighbor to the key of user.
Okay, so visited user, right?
Yep. And then we got
And
to add it. So it's dot
push.
append.
Oh, we're doing append on this one. Okay.
Yep. So we're adding it to the user and we're appending the
Get out of my way. Neighbor, okay.
yes. And then outside the while loop, we return. Actually, I think we've already got it written down. Return visited.
Okay.
Doo-doo-doo-doo-doo-doo.
Woohoo!
So that was easy, right?
Yeah. Now explain.
Almost too easy. Okay. So visited is a dictionary, right? So first thing we have our dictionary. This is just like we had last time. We're creating our paths. So we pass in the self because it's class, and the
Yeah.
user ID is the vertex that we're starting at. Okay. So first we create a stack. And then we have a secondary function of get neighbors. If we had imported the graph, we would have done the same thing, but we can just make a little slide function right here. Get neighbors, return self.friendships ID. Boom.
Yeah. That was easy.
Yeah. So we're basically holding on to this up here. We're just holding this little holding box. So then we're going to take the user ID and we're going to add it to our stack. And for every user in our stack, we're going to pop it out the back. All right, so that's our user. If the user is not in visited, we're going to add them to our visited. So again, we had K, remember, was our user ID. So our user ID is now going to go into our visited as the key, right?
Okay. Okay,
With
because that's where I
initial
was
value.
that's where I was getting lost at. Because we went and did user, but then we were making a list.
Yes.
Which visited was originally a dictionary. So that's where I was kind of getting lost at.
Yeah, this is where this right here, visited user, we're making the key. That's why I kept saying the key. The key is now the user that we just put in here.
Okay.
So this would be like user 1, Tiffany, Bob Jones, user 52, whatever their name is. The key is now the user.
That's right, because vertexes can have, or vertices can have multiple values within the key.
That's right, multiple weights.
Or weights, yes.
Yeah, they can, vertices can be connected to multiple vertices. So a singular vertex can have multiple edges.
Yeah.
Right?
Yeah, okay.
So in our binary search tree, our node could only have one of two pointers, left or right.
Yeah.
In our linked list, we either had next or previous. In this, we have 1,052 edges.
So then for each user, they're going to have more key value pairs.
That's right. And each user will be its own key.
Okay.
Right? So we'll have our key, like, so let's use some names. So if we were using names, then our user Bob would be a key. And his values would be all of Bob's friends. Bob has 2 friends because we run out of space. Our user Val, that's a name, will also be a key. And she's going to have a whole bunch of friends because we're not going to run out of space too soon. I'm going to be better at this. So she's probably also great at computer science. That's why she's got so many friends. So we have keys and the values are, oh, hey, look, Val is friends with Bob. Bob is likewise friends with Val. They can be on each other's lists, but we're not going to have 2 Bob keys, right?
Yeah.
So
It's
that's
just,
what we're looking for.
yeah. From Val will point to Bob, and then Bob will point to Val.
Right. They will have a connection.
Yeah.
All right. So then that's what we're doing here is for every neighbor that we get off of them, our visited user, we're going to append the value of our neighbor. So that's what we have. Val had the neighbor Bob, and then also Terry and Phil with a P and Kat with a K. So those are her friends. And then later on we get Bob. And Bob is friends with also Val with a V and Terry with a T and Corinna with a C. So we have all of these values.
Before, remember?
Yeah.
You just
So
get an extra friend.
yeah. It's like, remember we have one friend here and one friend here. We got so many friends. We have 2 friends in common. Valerie's got friends with Bob and Terry, and Bob is also friends with Valerie and Terry. I don't know, looks like some kind of creepy love triangle. So we have that's what we're doing. Does that make sense?
Yeah.
And then after we're all out of neighbors and no more friends left, we're going to return our visited, which is going to be our key value pairs of our friend and all of our friends' names.
Yeah.
Woo! All done?
Yeah. Got it.
Got it. Okay, cool. That's really it.
Okay.